So, in the last class, we have seen the distinction between preemptive scheduling and non-preemptive scheduling, right. So, in preemptive scheduling, the operating system can preempt a task when a higher priority task arrives. In non-preemptive scheduling, once a task has been allocated a resource, then that will continue till completion, or that task itself requests for some IO. Now, we will keep and also we discussed that shared access to resource can block the different tasks, but we will come back to that point a little later. Today what we will be doing is, we will be looking at the different scheduling algorithms that are used for real time operating systems. Okay. We are aware of the different scheduling algorithms that are used for normal non embedded system or non real time system type of scenarios. We are aware of the first come first served, shortest job next, round robin, etc. All right. But under preemptive scenario, when we try to schedule within a deadline, then we need to be a little bit more careful. So, if we look at a real time task here, for example, here we are showing a real time task. You can see a task is characterized by a period P and an execution time E. E is the execution time, all right. So, this is the execution time and P is the period. Period means the delay or the frequency at which a particular job arrives. Okay. So, right now we are considering only periodic tasks, we are not considering aperiodic tasks or sporadic tasks. Aperiodic tasks are tasks which arrive not at fixed periods, all right. For example, if this be my timeline and a task arrives at a regular delay, say 5 units, this is one arrival, this is another arrival, this is another arrival. A task arrives in regular interval, then it is a periodic task. Aperiodic task, this task could have been aperiodic if it had sometime appeared here, some with a delay 3 maybe, and sometime appeared here, like that. All right. Now, we are concerned with the periodic tasks only for the time being, and a periodic task therefore has a period, that is a delay gap, after which it appears, and it has got an execution time. Now, a couple of things need to be mentioned about this execution time. A priori, often we do not know what will be the exact execution time of a task, because that may depend on the arrival of some events, or that may also depend on some particular data. Therefore, when we talk of execution time, we talk of worst case execution time, all right. Usually we talk of worst case execution time. Now, since it is periodic, the jobs will repeat regularly. Okay. Now, the period is the inter release time. Now, a point is, say the job has been released at this point of time, and a job comes with a deadline, all right. The deadline is the absolute deadline, that come what may, the job must be finished by this time. And the worst case execution time of the job has been shown here. So, this is known as the relative deadline. Relative deadline means maybe that the job has actually been generated here, might be the job has been generated here, that is arrived or generated, but I release it from this point. Okay. Now, in real time scenario, I that is why this is known as the relative deadline, because this is a deadline with respect to the time when the job is being released or the job is being. Now, these two usually are the same for the case of an embedded system, but in general we can see that a job has been arriving in the ready queue, but it has been taken to some other queue and all those things. Therefore, with respect to the deadline, with respect to the release. So, the absolute deadline is given in terms of some time that it must be completed within 5 milliseconds. Now, that 5 millisecond will be computed from this point, the job is that is released. Now, the execution time is the worst case execution time or the maximum execution time. Now, it cannot be more than the period, obviously. In that case, there will be problem, and we are talking of something called the utilization of the processor. Say for example, during this time, this is the period, and during this period E units of time are being utilized for executing this job. Therefore, the utilization is E by P, E divided by P. All right. So, now we are associating a job with respect to, till now we have not talked about priority, but along with that each job that comes will come as a with some priority. Okay. So, with this notion of execution time, period, utilization and the deadline, let us move to the issue of real time scheduling. A real time scheduling or real time scheduler, it will determine the order in which the real time tasks will be performed. Okay. There can be two types of scheduling. One is static priority scheduling, that means the priority of the jobs are decided a priori. I know that this job will have this priority. Now, what the priority will be, that will vary, how the priority will be associated, that will vary from scheduling algorithm to scheduling algorithm. Okay. The other thing is dynamic priority scheduling, where we change the priority gets changed. Okay. So, we will study both this type of scheduling. Another very important concept that we must understand is the schedulability. Schedulability means that given a set of tasks, a set of tasks have been given to you. Now, these tasks have come with their execution time and with their deadline. Now, given this bag of tasks, are they schedulable? Does there exist a schedule? Whether I can find it out or not is a different question, but does there exist a schedule that can schedule all these tasks so that the deadlines are met? Okay. That is known as the schedulability. That is a property indicating whether a real time system, or that means a real time system means a set of real time tasks, can meet their deadline. Okay. So, here we are showing a 3 task scenario, and let us try to understand this diagram. This is task 1, this is task 2 and this is task 3. Task 1, as we can see, has got the execution time is 1. So, each of these tasks are being denoted as P comma E, where P is the priority and E is the execution time. So, now this priority, or rather period and the execution time. You see that for this job the period is 4, that means it is appearing here. Okay. Next, after 4 units of time, it is appearing again. Here are my time charts. So, it is appearing here, then here, then here, then here, after 4 units of delay. This one has got an execution time of 2 units and its period is 5. 1, 2, next appearance, next appearance, next appearance. Okay. And why are these arrows, if you can see them, these arrows are bidirectional? The reason is, this is also their deadline. The priority and the deadline of the jobs are this. For the second job, it must complete within the period, otherwise obviously you understand this is a simplistic scenario. The deadline can be less than this, but cannot be more than this, because then the second instance of this job will appear. Similarly, for this, the period is 7 and the execution time is 2. We will come back to this scenario again. We will explain or try out different scheduling algorithms on this set of tasks. All right. Now, we first start with, now this is a task scenario and we will have to decide on a particular type of scheduling. First, we will study static priority scheduling. Say here, we are considering a static priority scheduling, where it is a preemptive scheduling based on the priority. Okay. Our assumptions are as before, the tasks are periodic. Okay. No aperiodic or sporadic tasks are coming, that it is coming all in a sudden and never again. The job deadline is the end of the period. That is what we are assuming here, that since it is a static priority, we are assuming that the deadline is the end of the period. And a very important thing is here, we are not considering any resource constraints. In the last lecture, we are talking about mutual exclusion and shared resource. We were needing to share a resource because there were not ample number of resources, but here we are assuming that no job will be delayed because of non availability of resource. All right. The tasks are preemptible. Right. We introduce another term here, that is the laxity of the tasks. Laxity or slack, it goes by two names, laxity or slack of a task. For example, suppose a task arrives here and the task deadline is here, and the task execution time, it finishes within this time. The CI is the execution time. All right. Then this is the period that I have got at my disposal. Okay. This is known as laxity. All right. So, laxity is the TI, the time, that is, if I take the deadline and the current time plus how much time, this is the current time, right, this T, and it is taking so much time. So, T plus CI, there is no need of being CI time, CI, and this is deadline. So, if I subtract this, then I will get the slack. Okay. So, this term will also come in handy, the laxity, later. So, with these definitions and ideas, let us move to the first scheduling algorithm, which is the rate monotonic scheduling algorithm, all right, or the RMS. Again, we come back to the task that we had seen earlier. Now, here it is a static priority scheduling. The priorities are known beforehand. Now, what are the priorities? It assigns the priority according to the period, all right. And we know that we have assumed that the period is the same as the deadline for the time being. So, a task with shorter period has a higher priority, that means its deadline is less. Okay. So, it will execute, select a job with the shortest period. Now, I would request all of you to note this task specification down, and we will see what happens as we proceed with the scheduling. Now, you can see, you just note down 4, 1, 5, 2, 7, 2. From there you can reconstruct this. Okay. Now, you can reconstruct this. Now, if I look at this point, which one will have the highest priority? The one whose period is the shortest. So, the period is shortest for task T1, if I name them T1, T2, T3. So, therefore, I will schedule this one first. So, as I schedule this one, the other two will be delayed, although they arrived here, they will be pushed back. So, what will be the scenario? If we do this, so the first task T1, which was having 4, 1 and whose 1, 2, let me just put the timeline first, 4, this is its second arrival time, all right. This is 1, 2, 3, 4. Now, this task has finished here, and task T2, which was having 5, 2, was waiting here. So, again 1, 2, 3, 4, 5, it will again appear here, right, task 2. Now, the second task will start from this point onwards, because this has, I am assuming, by the way, a single processor. Okay. Therefore, this task will start and its priority is highest. So, it will take 2 units of time and will run here. Now, task T3, which requires 7, period is 7, therefore, 5, 6, 7. Now, this can be started here, right. Now, so I can start this task here. It will take 2 units. So, I start it here. I go on doing this, but something happens at this point. What happens at this point? Task 1 again arrives, and according to my priority, task 1 has got the higher priority. So, task 1 will execute here. Till then, till this task 1 arrived, this one has run, but it is supposed to get the other slot. It needed 2 units, 1 unit it has got, it will need another unit, but right now it cannot take. So, now task T1 has finished, but task T2 has arrived. Therefore, task T2 will now go for 2 units. And this task can only come here, and that means what? This task has missed the deadline. Right? So, the deadline has been missed. All right. Now, suppose I just change the scenario. I change the scenario, I make this period instead of 7, I make this 10. Now, what happens? Fine. So, this is 2, 1, this was 7, 8, 9, 10. Its actual period was here. Therefore, its deadline is also this. Therefore, now both of them are schedulable. Therefore, the question is, how do I know that given a pack of tasks, whether I will be able to schedule them or not? Okay? That is something we have to understand. So, we will try to find that out. It has been found. Is the problem clear to all of you? This problem is clear? All right. So, but with this I do not miss the deadline. So, it is schedulable. Okay. Now, it is said that a set of n tasks, is schedulable on a uniprocessor by the rate monotonic scheduling algorithm if the processor utilization is this. What is this? Ci is the execution time of the task, of one task, Pi is the period of that task. If, and we have seen that Ci by Pi, we had given a name of that was utilization. So, the total utilization for all the tasks, this is the total utilization, is less than equal to n times 2 raised 1 by n minus 1. If this condition is satisfied, then we can schedule the tasks. I am not going into the derivation of this. This derivation can be found out from the there is a famous paper by Liu and Leyland. Those of you who are interested can look up the paper, and it actually comes from the response time analysis, and from there we get this. We will illustrate the significance of this condition shortly. Now, this condition is sufficient, but not necessary. That means, if this condition is satisfied, then certainly you can schedule it. There exists a schedule, but if it is violated, then a schedule may exist or may not exist. I do not know beforehand. Okay. So, now let us take a case. I will come back to this. Let us take a task scenario where I have got a task T 1 whose time is say 4 is the period, 1 is the execution time, T 2 is another task 5 2, a little different I have done from the earlier one, and T 3 is 7 2. There is the same thing, the earlier task, it failed. The task that we had just now done, okay, this scenario, this task scenario that failed. All right. We are trying to analyze that with respect to the utilization criteria. Now, what will be my sigma u? I have got sigma u or u is sigma C I by P I, and that will be here 1 by 4 plus 2 by 5 plus 2 by 7, right. So, that is coming to around 0.95. little more than that, little less than that, however. Okay. Now, we know that this should be less than equal to n 2 raised 1 by n minus 1. Now, for us n is n 2 raised 1 by n minus 1, that is 3 tasks. I had 3 tasks, 2 raised 1 by 3 minus 1, that comes to around 3 into 1.26 minus 1 is equal to 0.78. So, you see this condition is not maintained, is violated. Okay. That means, what does this thing, what is the insight that you get here? The insight that you get here is that if there be 78 more than 78% utilization of the CPU, then you cannot schedule more than 3 tasks here, right. Now, under this scenario, now you can say, for example, if I make it 10 to, what will this thing become? This part will be modified to 1 by 4, 2 by 5, that is 2 by 10. So, that is coming to 0.25, 0.4, 0.2 is coming to still this is more, but I could schedule. Therefore, this condition is sufficient, but not necessary. Even with 10 to I could do this. Okay. But if this is violated, I can say, I mean, if this is satisfied, rather let me put it in there. If this is satisfied, then I am sure that I can schedule them. Okay. So, let us take another example of this. Let us take another example of this. Suppose I have got, pardon, any questions? Okay. So, let us take another example, a task set T 1, which has got is 2 4. I am sorry, writing it in a different way. It is 4 2, and T 2 is another task, that is 8 1. All right. Now, let me do the schedulability check here first. What does the schedulability check tell me? The left hand side of utilization will be 2 by 4 plus 1 by 8, that is 0.625, right. Whereas, the other side will be 2 times root 2 to the power half minus 1, that will be 0.82. This is less. So, I am sure I will be able to schedule it. Okay. I can just say surely I can schedule it. All right. Therefore, now let me try to schedule it here. Which one? What will be? That is a revision of the rate monotonic scheduling algorithm I am trying to do here. So, which one has got the higher priority? T 1. So, T 1 will come in and T 1 will take 2 execution units. Say this is 1, this is 2, this is 3, this is 4, 5, 6, 7, 8. So, first T1 will take place. So, T1 will take 2 units. T1 has executed. Now, T2, now T1 comes again here, this is the arrival time of T1 after 4 units. Again 1, 2, 3, 4, again T1 comes here, and T2 comes after 8 units. So, and takes 1 execution time. So, 1, 2, 3, 4, 5, 6, 7, 8. So, T2 will also come here at 8 and this 4. Now, T2 is being scheduled here and T2 will take 1 unit. T2 has executed here. Now, during this time nothing is there. Now, at this point which one is the active task? T1. So, T1 will take again 2 units, 1, 2. Now, what will happen? Now, all the tasks are complete. So, T2 and T1 both are complete. Next instance, when will T1 come? T1 is arriving here and T2 is also arriving here. So, which one will have priority? T1, right. So, T1 2 units, it takes 2 units. T2 arrived here, but T2's deadline is much later. So, T2 can very well get its place here and no one misses the deadline. That is because the spread, the T2's period was so large, therefore, I can certainly schedule it. That is the significance of that condition. All right. So, given this, now, if in the earlier example, I had just made a change, you just do this, that I am giving again 3 tasks. T1 is 4 1, T2 is 5 1, I am changing it a little bit, T3 is 10 1. All right. It is an assignment, I am keeping it as an assignment. All right. Test the scheduling criteria, whether it is schedulable or not. If it is schedulable, find out a schedule. Okay. Under RM, under rate monotonic scheduling. Now, so what happens is, if I just draw a curve, we have got this sigma C I P I should be less than n 2 raised 1 by n minus 1. Now, this as n tends to infinity, this part tends to RHS tends to log of 2, that is around 0.69. That means, so the curve, if I have the number of tasks n going on this side and the utilization u, this is the utilization u on the other side, then if I start from 1, then gradually it 1, say this is 0.9, 0.8, 0.7, 0.6, like that it comes out. The curve will come down to something like this. That means the maximum number of tasks that I can accommodate and schedule is limited by the utilization of the I can, as the utilization comes down, the number of tasks, as I increase the number of tasks, the utilization comes down, and so up to this level. So, if it be below 70%, we can certainly schedule it. Okay. That is under rate monotonic scheduling. Even beyond that, it depends on the idiosyncrasies of the tasks. Okay. In the following lecture, we will continue with another scheduling algorithm, that is the earliest deadline first.